Okay, in this podcast we're going to take a look at the reaction quotient, which is very similar to the equilibrium constant. Okay, so we use the reactant quotient to determine if the reaction is at equilibrium or not, and if it's not, what needs to happen to get it to equilibrium. So we are given a set of concentrations for a reaction of both reactants and product, and we calculate Q the same way we calculate K, and then use that Q to determine whether or not the system is at equilibrium. And if Q and K are the same thing, we are at equilibrium. So we use it when we don't know whether or not we're at equilibrium. So let's take a look at an example. So here we have 3 examples, and let's assume that we have this reaction where reactant A becomes product B. And Q is calculated exactly the same way as K is. It's the concentrations of the products over the concentration of the reactants. And in fact, if these had coefficients, they'd be there as the superscripts. So if we have Q, let's say Q is 1.3, we calculate that ratio of products over reactants. And what we see is it is less than K. So what needs to happen in order for us to reach equilibrium is we need to increase the products so that this value becomes bigger, right? We increase B while we decrease A, and so therefore increasing B means that we are shifting the reaction to the right, and the reaction is going in the forward direction. Okay. Here we have Q is larger than K, which means we have more products than we should have compared to the reactants in order to be at equilibrium. And if this is happening, if we have a larger Q than K, that means that the reaction is going in reverse. And if we calculate Q and it comes out to be the same as K, that means we are, in fact, at equilibrium. So we use this reaction quotient Q when a system is not at equilibrium and we don't have equilibrium concentrations. So if we had a more complex equation, reactant A and B making products C and D, the reaction quotient is exactly the same calculation as it is for K. Let's say KC. Okay, but the concentrations are not necessarily at equilibrium. Okay. This got a little bit messed up, and let's move over to the dossier for making the podcast. But let's imagine we have this continuum where we have reactants on the left and products on the right. And if we just think from 0 to higher numbers, if Q is less than K, then in order for Q to get to K, we have to shift to the right. So we have to be making more products. If Q is equal K, so this is reactants and products, and Q and K are the same, then we're at equilibrium and nothing's going to shift. Of course, we are at dynamic equilibrium, which means we reactants go into products and products go into reactants at the same time. The reaction has not stopped, it has just reached a point where the concentrations are stabilized. And then we could also have a situation where our Q is greater than our K, and when that happens, in order to get back to K, back to equilibrium, the reaction has to go towards the left, and the reactants are going to be favored. Alright, so let's take a look at an example. We have a reaction that has an equilibrium constant of 0.078 at 100 degrees C. If the initial concentration of each of the 3 substances, this, and this, are all 0.1 molar, which way will the reaction proceed to reach equilibrium? So go ahead and try to answer that and then come back. Okay, so let's write the formula for Q. So Q is going to be the concentration of SO2 times Cl2, and they have coefficients of 1 over SO2 Cl2, and that's also to the 1, right? So that's going to be 0.1 times 0.1 over 0.1, which will give us a Q equals 0.1. Okay, so my Q is 0.1, my K is lower than that, 0.078. So if I imagine I have reactants here and products here, I'm sorry, let's go back. This is my K, this is my Q. So my Q is greater than 1, so in order to get to K, I have to go left. So the reaction is going in the reverse direction. Okay. Alright, so let's take a look at this example. For the synthesis of ammonia at 500 degrees C, the equilibrium constant is 6 times 10 to the minus 2. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. Okay, so the first thing we have to do is write the balance equation. So I have N2 plus H2 gives me ammonia